Hey everybody, welcome to our next video in the gas laws unit, which is all about one of the most important equations in all of chemistry, which is the ideal gas law. If you talk to anybody that has studied chemistry to some extent, not just a high school chemistry course, but even in college, they most likely remember talking about the ideal gas law and can probably tell you what the ideal gas law is. So the ideal gas law tells us the conditions of a gas depending on how many moles of the gas there are, or the volume of that gas, and the temperature, under a bunch of different conditions. I'm just going to give you the definition here rather than talking about it anymore. So it's a mathematical relationship of pressure, volume, temperature, and the number of moles of a gas. So we already know that 1 mole of a gas at STP, standard temperature pressure, 1 atmosphere, 273 Kelvin, takes up a volume of 22.4 liters. What if I have a half a mole of that gas? What would be the volume at STP? You might be able to figure that out. All right, well, half of 22.4 is 11.2. Okay, easy. But what if I have a gas at some other conditions? What volume would that take up? What if I have a different number of moles of the gas? This particular equation, the ideal gas law, takes all of that into consideration. And that equation is PV equals nRT. So you recognize probably quite a few of what these variables mean. So P, of course, is the pressure. Now, in the other gas laws we've talked about, it didn't matter what units pressure was in. In the ideal gas law, it matters. Pressure has to be in units of atmospheres. And that's because if I look at this new constant, which is this capital letter R is what we call the ideal gas law constant. So this value is going to be the same in every ideal gas law problem that you use. This value is 0.08206. I hope I said that correctly. And the units of this are liters times atmospheres per mole Kelvin. I think this is written a little bit nicer in your notes because I wanted you to really see the units there. But it's liters times atmospheres divided by moles Kelvin. So because we have atmospheres as this unit for R, for the unit of pressure in R, we have to make sure that our P is also in units of atmospheres. Volume must also have a particular unit, and the volume must be in liters again, and that's because R has this specific unit of liters in there. N is the number of moles of the gas. R is the ideal gas law constant. And T, of course, is the temperature of whatever temperature this gas is at. This is what tells us if I have some conditions of a gas, what volume would it be? If I have some volume of a gas at this pressure and this many moles, what would the temperature be if it were an ideal gas? There is another equation if it's not an ideal gas, but we don't want to get into that because you have to look up constants and you have to do all this crazy stuff, which I'm sure you're not interested in. So we just deal with the ideal gas law. Anyway, rather than talking about this anymore, let's go into some sample problems in the notes together. All right, so sample problem 11. Looks like we have 4 examples here. We're not going to do, or I'm not going to do all 4 of these with you because like I said, I think they're pretty self-explanatory. As long as you have all of these variables in the correct units, you should be able to solve each of these pretty easily. And in fact, sample problem 11A is that way. It looks like the only thing we're going to have to convert is the temperature. But anyway, we want to know what pressure in atmospheres. So what pressure is what we're looking for. So P equals something is exerted by 3.25 moles of hydrogen gas. So I'm given the number of moles. It's 0.325 moles in a 4.08 liter container. So that's the volume, 4.08 liters at 35 degrees Celsius. So T is equal to 35. And when you're using the ideal gas law, always just double check to make sure your units are correct. So P is what I'm solving for, so I don't have to worry about that. I am given the number of moles, so this is good. Volume is in liters, so that works. Temperature does have to be in Kelvin, so let's just add 273 to this 35, and we get 308 Kelvin. The reason why, like I said before, you have to have all of these in particular units is because of this ideal gas law constant right there. So that has very specific units of liters, atmospheres over mole Kelvin. Which is why in Boyle's law, Charles's law, Gay-Lussac's law, it doesn't matter. However, for the ideal gas law, it does. Now that we have everything in the correct units and we know R, because R is always that number, we can just go ahead and plug everything in to our ideal gas law. So pressure, we're going to leave P there because that's what we're trying to find. The volume is 4.08 liters. Number of moles is 0.325 moles. R is 0.08206. And that again is liters times atmospheres per moles times Kelvin. It's got really crazy units, but the units actually work out as well. I'll show you that in class because I want to try to keep this as short as I can, these videos. I say that, and the last one I did was like 40 minutes. So anyway, trying not to add more than I need to. If you solve for this correctly, actually I could quickly show you units here because look, I have moles on top right here, and in R, moles is on the bottom, so they cancel out. Kelvin right here is on the top, and that Kelvin cancels. And when you divide, your units of liters cancel out. So you're actually just left with units of atmospheres. And when you do that, your quantitative value, so your numerical value, should be 2.01. And you are left in units of atmospheres, and you could just memorize that. Or, like I said, the units actually work themselves out as well, because the only thing you're left with is units of atmospheres. So you go ahead and try B. It's the same exact thing. As long as you get the algebra right and you plug everything in the calculator correctly, you should get the right answer. Go ahead and try B. Again, it's just using PV equals nRT. The only thing you have to convert is that temperature. So pause this video, try 11B. So your answer should be 32.9 liters. Again, because you're solving for volume, the way the units work out, you should get volume in liters. I don't always write my units out for R just because I find it very tedious, and there's a lot of very tedious things in chemistry. And although you have to do them sometimes, this one is one I don't recommend always doing. I just write the units of R, and then as long as you know the units for whatever variable you're solving for, you're good. And that's it. So that's the ideal gas law. Again, you have a gas because we know that 1 mole of a gas at STP takes up a volume of 22.4 liters. This equation is allowing chemists to know at different conditions what would one of those other variables be. So very useful equation. Let's try C, so a little bit different. How many grams of carbon dioxide, so how many grams of CO2 are there, let's get some of these things down here, in a 45.1 liter container at 34 degrees Celsius and 1.04 ATM. Now, so of course I have PV and I don't have the number of moles. That's the only thing that's missing. So in this case, we actually have to solve for the number of moles and then convert your number of moles to the mass in grams using a simple mole relationship like a Chem 1 problem, just using the molar mass. And what you're going to find in a couple of minutes is that you could solve these ideal gas laws in so many different ways. There's actually 2 derivations that we can build off of this as well. So anyway, let's just go ahead and solve this one together then. So we're going to use PV equals nRT. Before we do anything else, let's just convert that temperature to Kelvin, and it should be 307. So I have 1.04 for pressure. I have a volume of 45.1 liters. Trying to find the number of moles. I have R. Again, I don't always like to write the units for R, so I'm just going to write the number. And then I have the Kelvin temperature. And when I solve for that, your number of moles is 1.86. 1.86 moles. And the compound is CO2. The question is not asking for how many moles of carbon dioxide. It's asking for how many grams of carbon dioxide are there. So once we get the number of moles, really relates everything to everything else in chemistry. So let's just do a really simple mole conversion. Moles of CO2. And we'll go 1 mole of CO2 on the bottom. And then you could just find the molar mass for carbon dioxide, and you should know how to do that at this point. And that number is 44.01. And when you solve for that, you get 81.9 grams of CO2. So sometimes you'll have to kind of take this one step further, like you'll see in the next couple of, in the next sample problem, what I mean by that. But in this case, it's pretty simple because you could just do a simple mole conversion. What I want you to do is you try sample problem D. So it looks like you have to work backwards from the one before. Watch your units with this one. I do notice students get a little tripped up just by units. So make sure you're aware of what units everything is in. Pause this video and try sample problem D. And there's your answer there, 0.893 atmospheres. I'm sorry, my work looks sloppy sometimes. Sometimes this pen gets pretty sensitive and I have to like rewrite things a whole bunch of times. So this was the best I could do as I was solving this problem. I noticed with this one, a lot of times students forget to convert the milliliters to liters. So if you got an incorrect answer, if it's off by 3 decimal places, that's probably where your mistake is right there. And you don't have to show work for that. You could just divide by 1,000. I'm confident you all know how to convert milliliters to liters or vice versa correctly. And temperature was already in Kelvin, so you didn't have to do anything with that. So there's your correct answer. Like I was saying before, so as you're solving a lot of these problems in chemistry, you're going to find that there are a lot of different ways to solve the same exact problem. We could all have a different approach to solving a problem, and we could all get the same answer as long as the math and the chemistry all make sense. So what I want to show you actually is how to introduce 2 new variables into the ideal gas law. And we're going to introduce the molar mass, which we're going to use the letter M, a capital letter M, for molar mass, as we also see down here. And we're also going to convert density from that as well. So just the density, which we're going to symbolize with a capital letter D. And I'm going to show you how to derive these 2 units from the ideal gas law. You will not have to replicate this on your own, but I always like to show how to derive these new equations because when I took some of my college chemistry classes, I had to do this a lot, and my professors always would show us the derivations. So let's just go ahead and start off with PV equals nRT, which of course is the ideal gas law. We are going to solve for the molar mass in this case. So we're going to show you the derivation of molar mass and density. So we're going to somehow introduce molar mass into this and set the whole thing equal to that. Well, the variable that I would have to manipulate in order to get the molar mass is the number of moles right here. So we're going to have to start off with that variable. And to introduce the molar mass, just by thinking about Chem 1 and mole conversions, we know that we can find the number of moles of a gas by taking just the mass of that sample, whatever the mass is. You know, you have 0.3 grams like the problem before that said, and you divide that by the molar mass of the gas. So let's go back to this one up here. So again, I have the mass in grams divided by the molar mass gives you the number of moles. So that's what I'm showing here, but just with letters instead of an actual problem. So what we're going to do is we're then going to just make a substitution and plug in the mass of the gas over the molar mass in for N right up here. So because those are equal to each other, I'm going to substitute that into PV equals nRT. So PV equals the mass over the molar mass times RT. Now, you can go ahead and solve for this, but a lot of students don't always like to work with fractions. So we're just going to get rid of that fraction, and we are going to set this whole entire thing equal to molar mass. So to do that, let's go ahead and just do some algebra right here. I'm going to multiply, so because these are technically over 1, let's just multiply these by one another. So the mass divided by RT, it's an R, over the molar mass. And again, if I rearrange this a little bit, if I multiply both sides by M to get rid of this, we want to isolate M. That cancels out. We get the molar mass of a gas times its pressure times the volume gives us the mass times R times T. However, if I want to get molar mass, make this whole thing equal to molar mass, and I divide both sides by PV, and you get this final equation that the molar mass of a gas is equal to the mass of that gas times R times T over PV. So I want you to put a box around this equation right here. You do not need to know the process on how to do that. I just wanted to show you how I got this equation, because you could derive new equations from old ones. So this is just another expression of the ideal gas law, that the molar mass of a gas is equal to the mass of that sample, whatever's in the container, times R times T over PV. So this one, again, is important. We're actually going to use this equation in a lab. And then let's say you have the density. In this case, you want to find the density, or you're given the density and you want to know some other variable. You can also use that, because if you look at this equation, there's density inherently in that. Let's just go ahead and I'm going to rewrite this equation up here, and I'm going to solve for density on this side here. So M equals MRT over PV. You might remember, hopefully you remember, that the density of something is equal to the mass of that object divided by its volume. And if I look back at this equation, the one that we just derived, look, I have M divided by V. I have density in this equation. So what we're going to do is substitute M over V in for D, right into this one up here. So what we can do first to make this a little bit easier, let's isolate this out here. So the molar mass of a gas is equal to M divided by V, so there's density, times RT over P. let's just go ahead and plug density in for that. So molar mass of a gas is equal to the density of that gas times RT over P. Again, we want to solve for density. So we're going to isolate density on one side. So at this point, we're just rearranging this equation a little bit. So I'm going to do what I did before and just start to solve this algebraically. So the molar mass is equal to, because this is technically over 1, dRT over P. Again, we want to isolate that D. So I'm just going to multiply both sides by P first. And you could do this however you want to. Ultimately, it doesn't matter. Is equal to PM. The pressure times the molar mass is equal to density times R times T. And then to isolate density, let's divide both sides by RT. So density is equal to the molar mass of a gas times its pressure divided by RT. This is also the ideal gas law. This is the ideal gas law. This is the ideal gas law. And PV equals MRT is also the ideal gas law. They're just different ways of solving the same equation. It's all the ideal gas law. So you don't have to really memorize every single one of these equations, but you can, just by knowing a little bit about this. So, okay, well, I know the number of moles, and if I know moles is equal to mass divided by molar mass, and then the density is equal to mass over volume, whatever, you could solve this however you want. So again, there's really no right or wrong way on how to solve any of these following examples. So here's what all of those variables mean down below. And here are just 3 examples of using those 3 equations. There is no right or wrong answer as to what equation you should use. As long as you are solving it correctly, that's all that matters. Personally, if I were to go ahead and start to solve sample problem 12, I know that molar mass is in units of grams per mole. So we know that our final answer has to have those units in grams per 1 mole. Solve this however you want, it doesn't matter. We're just going to go ahead. I helped you derive those other equations. So let's just use one of those equations we just did. What is the molar mass of a gas? If 0.427 grams occupies a volume of 125 milliliters at 20 degrees and 0.980, we have an equation that actually solves for molar mass right here. So let's just use that equation. Again, it is the ideal gas law. It's just another derivation of the ideal gas law. So the molar mass is equal to the mass of the sample times R times T over PV. So we're solving for big M here. And I'm actually not even going to write all those variables out. So capital M is equal to, that's what I'm trying to find. Sample, the sample contains 0.427 grams of this gas, times R, which we know is always 0.08206, times the temperature. So we are at 20 degrees Celsius here. So we are at 293 Kelvin. Let's go ahead and divide this by the pressure, which is 0.980. And the volume it occupies is 125 milliliters, but don't forget to convert that to liters. And again, the units for this also work out. I'll probably show you this in class because, again, I don't want to make this video too long, although it's probably pretty long as it is. Your final answer is 83.8 units of grams per mole. Again, this is the ideal gas law. So you could actually use PV equals nRT. This is probably how I would have done it. You could use PV equals nRT, solve for the number of moles, and because you have the mass, I would have just taken 0.427 grams and divide it by whatever I got for moles, because I know that the molar mass has to have units of grams per mole. Just one example how there's not one right way, one wrong way how to solve this problem. Let's go ahead and try B. So what is the density of a sample of ammonia gas if the pressure is 0.928 and the temperature is 63? So again, there's no right or wrong way to solve this, but we do have an equation that we can use to just directly solve this. And that's the density is equal to the molar mass times pressure divided by RT. So let's get that written down here so we have it more readily available. D equals MP over RT. So what's the density of this gas? We do have to calculate the molar mass for ammonia, and ammonia has a molar mass of 17.04. Don't forget units. And one thing not to forget is that molar mass is always in units of grams per mole. Try as best as you can to get that ingrained in your brain, because that's really important to know. Times pressure over R times T. So 63 plus 273 is 336. And when you solve for this, so you should get an answer of 0.574, and units for density are grams per liter, grams per liter. That's because your mass is in units of grams. We could see right there. And then actually R has that unit of liter inside of it. So I'll show you how to work out the units in class, because it's not necessary you know that, but it is a good skill to know how to do. Try to do sample problem C right here. So using whatever equation you want, it doesn't matter, because again, it's all the ideal gas law. They're just different derivations of the same thing. Try to solve sample problem 12C. And there's our final answer there. So 32.8 grams per mole. Again, the way the units work out is you should get an answer of grams per mole. I'll show you something like this in class where we work through the units. That's it for the ideal gas law. So again, the ideal gas law is typically PV equals nRT, but we can also use these derivations of the ideal gas law to introduce molar mass and the density of a gas as well, which sometimes are much more useful than just PV equals nRT. But again, it's all the ideal gas law, which is why I wanted to include this in this video. Of course, if you have any questions, make sure you see me, ask me any questions in class, before class, whatever works for you, but please don't hesitate, especially when we're introducing so many more units and so many more variables in these problems. Anyway, I will see you in the next video soon, which is all about the stoichiometry of gases, and we'll actually finish off this unit with that one. So I will see you then, and have a great day. Bye.